Um, so hello everyone. It's my pleasure to be here today, presenting some of our recent research here in our team. In this opportunity, my presentation is about bimetallic catalyst for the hydrogenation of amides, from experimental to data-driven insights. Before going to the technical part, I would like to tell you a little bit about our company that some of you might not know yet. So this research is done in Syensqo, that this company recently born after the splitting from Solvay. Possibly some of you know more about this company, the Belgium company. So in our team, E2P2, that stands for Eco-Efficient Products and Process Laboratory. What we do is we do research in catalysis and simulation. We are an international team with complementary skills that deliver breakthrough innovation projects that we try to join the academy with the interests of our company. We've been running for about 15 years already, since 2011 that the laboratory was born. And during the time, we've been adding partners into our network. So here you can have a look the different institutions that comprise our team. So we are based in Shanghai, and we have also researchers from CNRS, and some of our partners are universities in China, like ECOST or Fudan University. Also others in Europe, like University of Lille, Poitiers, or Aix de Lyon. Okay, with this introduction, let's go to the topic. We all recognize that the amides are compounds used in a wide variety of materials, from polymers to even the paper industry. And for the specific case of amides, such as laurinamine, the traditional synthesis consists in a three-step process, starting from esterification, then hydrogenation, and finally amination. However, we are interested in a shorter route, only a two-step process, first amination and then hydrogenation of the amide into the amine. We're interested because we can produce the target amine in only two steps. So this is atom efficient, also green and more sustainable. But we also recognize that hydrogenating amides is very difficult, and the challenges arise because of the low reactivity of the amide group. Due to that, we normally require harsh conditions like high temperatures and pressures. Also, we have challenges in terms of selectivity, because not only we can break the carbon-oxygen bond that results in the amine, but we can also break the carbon-nitrogen bond, resulting in the higher alcohol. So in the literature, there are reports about the use of homogeneous and heterogeneous catalysts for this transformation. But for the case of the homogeneous ones, normally they consist in ruthenium complexes with phosphine ligands together with Lewis acid. And in those systems, normally the reaction that happens is the carbon-nitrogen scission, resulting in the alcohol product. In contrast, heterogeneous catalysts target more the production of the amine, and the state-of-the-art catalyst for this transformation consists in the combination of a reducing metal with an oxophilic one. The reduction metal activates hydrogen, while the oxophilic metal activates the amide, and these bimetallic catalysts. For instance, vanadium platinum, rhenium platinum are examples of bifunctional catalysts reported in the literature. However, the question we ask ourselves the question, which is the most active formulation? And we found in the literature important discrepancies. Some authors report molybdenum rhodium is more active, others vanadium platinum, others vanadium rhodium. So there is no consensus about which is the most active formulation. And in this project, we tried to rationalize which parameters govern the reactivity of these catalysts. So the objective of this project was to understand and engineer and the engineering of highly active catalysts. So in a normal project, we start by analyzing the available literature. So the conventional approach for research is the researcher, based on this analysis of the literature, would, based on chemical intuition, would prepare a series of materials and test them in catalysis, later doing screening and optimization. In our case, we tried to start by doing a data-driven approach. So after analyzing the literature, we prepare a reliable experimental data, and then this information was fed into a model, but we did some data analysis to draw some property and reactivity correlations to understand finally our system and draw some guidelines for catalyst design. So first, the preparation of the catalyst library. Okay, so I was saying that we prepare a benchmark catalyst so that we could compare our materials with the benchmark one. So here are the results. First, here you can see the model reaction where we tested our materials. Hydrogenation of lauryl amide to laurilamine using a typical batch reactor, and they're relatively tested the support effect. And to do that, we prepare a series of rhenium platinum catalysts supported on different carriers, magnesia, titania, hydroxyapatite, etc. And we found that the one supported on hydroxyapatite was the most active. Interestingly, if we plot the yield of the amine against the BET area of the support, we can see a sort of correlation where the most active one is the one with area, let's say intermediate area of about 60 square meters per gram. So from this, initially, we concluded that apparently the more suitable support displays intermediate values of area, possibly because this is the one that has the right trade-off between dispersion of the metal and particle size of the metal also. Next, we wanted to understand the correlations between the support and the metal formulation, and to do that, we prepare 4 catalysts. 2 of them rhenium platinum supported on titanium and hydroxyapatite. This is the one I just presented before. And we prepare a second formulation, vanadium platinum, supported in the same supports, titania and hydroxyapatite. And we expected to see a similar reactivity trend for the 2 supports. However, as you can see here, the reactivity trend is divergent. Vanadium platinum was more active in hydroxyapatite than in titania. So to understand this, the reactivity, we did characterization first, particle size by TEM and XPS. So in TEM, we observed that the catalyst supported of platinum. So here you can see the correlation between the yield and the particle size. While the others, the ones supported on titania, they had larger particle size. So this, on the one hand. On the other hand, we also analyzed the metallic platinum by XPS, and we observed that the supported on hydroxyapatite had a higher content of metallic platinum. So these together tell us that the catalyst is more active. The ones on hydroxyapatite, the reason is because the particle size is smaller. Normally, many catalysts, heterogeneous catalysts, have this trend because of the higher exposed area of the active metal, and also because of the larger percentage of reduced platinum, which would benefit the reduction and the activation of hydrogen. Now, one of the objectives of this work was to study the effect of the oxophilic metal. So to do that, we prepare a series of 17 bimetallic catalysts using in all of them the same reducing metal, platinum, the same support, hydroxyapatite, and we just changed the oxophilic bimetal. And we selected these among metals, transition metals from the groups 3 to 8 of the periodic table. And here you can see the results of conversion and amine selectivity. You can see there is a kind of periodic trend for the conversion. The most active oxophilic metals were vanadium, molybdenum, rhenium. And if we combine this information in this plot, we have amine selectivity against conversion. We can see that vanadium platinum was the most active catalyst, followed by molybdenum, rhenium. And interestingly, we can see some clustering of metals with periodic relationships. Like those close in the periodic table, they have similar performance. And this is not a surprise. Now, what we wanted to do next is trying to understand what is behind of these relations. So we tried to conduct a data-driven property performance relationship. So to do that, basically we tried to do linear correlations. So we identified and collected a series of descriptors which could be important for the performance. Then we did data normalization, remove some outliers, and then perform calculation of the Pearson coefficient between the conversion, for instance, and the descriptor. So now you might wonder what type of descriptors we used. So here I explain to you which one. So we started with, let's say, cheap descriptors such as physical or atomic properties of the oxophilic metal. As you remember, our catalysts, our series of bimetallic catalysts, they had the same support, the same reducing metal. The only difference is the oxophilic metal. So we focus in, let's say, producing descriptors related to the oxophilic metal. So these physical and atomic properties are of that oxophilic metal. Also, we collected some electronic properties like electronegativity, electron affinity, other atomic, such as the atomic radius, and also a bit more sophisticated descriptors, such as the DFT adsorption energy. For instance, the adsorption of oxygen to the oxophilic bimetal. In this case, we are assuming that the two phases, the oxophilic metal and the reducing one, are segregated. And we also consider the possibility of having an alloy, adsorption energy of oxygen on the alloy. Also, we included some dummy descriptors as random numbers as a control, and here the results. So in this plot, you can see the important features for the conversion. The most important descriptor was the adsorption energy of oxygen, followed by the electronegativity of Pauling. These results are, we can tell that they are statistically relevant because if we compare with the random number descriptors, dummy descriptors, well, there is an important difference. So that's how we can trust about our results. Then if we plot, if you can see here the correlation between the conversion and the adsorption energy of oxygen, you can see that there is a sort of linear correlation. And finally, the physical explanation of why the adsorption energy of oxygen could be important for the conversion boils down to the mechanism of this reaction. We know that one of the key steps for this transformation is the activation of the amide, which is in charge by the oxophilic metal. So apparently, oxophilic metals with the right balance um, of absorption energy of oxygen and electronegativity will be the ones that will perform better and will be more active. So in this case, we can see that metals that have a very strong absorption for oxygen, they are not good in catalysis. Conversion is very poor, while those with a relatively mild absorption for oxygen, they perform better. Okay, to conclude, in this work, we perform an experimental and data-driven approach to get insights about the catalysis design. So we got some guidelines for the preparation of highly active bimetallic catalysts for the hydrogenation of amides, such as supports with intermediate BET areas, and also in terms of the effect of the oxophilic bimetal for platinum formulations, we observed that those with relatively large electronegativity and weak absorption of oxygen performed better. Okay, so in the future, I would just like to tell that we would like to increase the size of our dataset, hopefully to be able to develop some machine learning predictive models. Of course, we need more data for that purpose. Okay, thank you very much, and I will be glad to receive some questions.